The next speaker is Alberto Petri from Roma, in stick slip dynamics in a sheared granular system.
Okay, good morning. At first I want to thank the organizers for the meeting and for the opportunity of staying here. The work I'm going to present is made, sorry, no, what's, okay. It's started within a national project on the rheology of granular medium, and then now is going on within a European project about triggering instabilities in materials and geosystems, which is made in collaboration with groups from Rome and the University of Edinburgh and the University of Helsinki, the University Joseph Fourier in Grenoble, and the Institute for Avalanche and Snow in Davos. And these topics in particular have been developed in the group in Rome. Stick slip is the subject of this work. Of course, stick slip takes place in many different situations besides in granular, and it's relevant in the fault dynamics where granular are present, of course, but also in solid and solid friction at the macroscopic level. But at a microscopic level in phenomena like plasticity. But we are interested, of course, on what happens in the granular case. We have set up an experiment in which you have glass beads in a channel which are sheared by a top plate which is driven by a motor and is connected to the motor by a spring, so that you have intermittent motion of the plate as a function of the resistance that the medium presents to the shearing. And the relevant parameters of the experiments are, of course, the driving angular velocity, the spring constant, torsion spring constant, and the inertia of the disc. This is an image of the realization of the experiments. Here are some of the parameters we used, and what you measure is the angle between the plate and the motor, which of course is a fluctuating quantity because of the stick slip motion, and the measurement is made by an optical encoder which has a rather high precision. And here should appear some, just to have an idea of the motion of the plate. Of course, depending on the driving, the motion can be much slower than this one, or also faster, and you can also enter a sliding regime in which the motion is continuous. But what we are okay, so you can distinguish in a regime at slow driving motion and with the weak stiffness of the spring, in which you have a stick slip regime, intermittent motion. So if you look at the velocity signal in time, you have something very erratic like this plot. On the other hand, if you increase the driving or the spring stiffness, you can enter a continuous sliding regime, which is the fluidized regime, in which you have the velocity presents a fluctuating but a continuum signal. So you can distinguish these two regimes, and these two regimes have very different statistical signatures, of course, besides the different velocity behavior. And for instance, if you measure the force, the reaction force of the medium to the shear, and you make the statistics, you can see that if you have Gaussian statistic in the collisional regime in the continuous sliding, but you don't have a Gaussian statistic in the stick-slip regime, and you have a very asymmetric distribution of the force, and which is rather stable with respect many parameters, and also is does not change very much if you look at reaction torque, at a static reaction torque in the stick phases, or to the dynamic force or torque. I speak about torque because it's a circular system, so, but I will say also force as well. And in the static or dynamic regime, you have a very similar distribution. So we want to concentrate, of course, depending on the choice of the parameters, you can also have a very periodic stick slip, but this is rather simple to explain, to predict, so it's not very interesting. But we want to concentrate on the irregular stick slip regime, and we want to characterize statistically these dynamics. So you can look at different quantities. One relevant quantity, of course, is the velocity, instantaneous velocity of the plate, and other quantities are the extension of a slip events. So you can integrate the velocity on the interval in which it's different from 0, and you have the angular extension of a slip event, and you also can measure the duration of a slip event, or you can measure the torque as I shown before. And what we want to do is to determine experimentally the probability distributions of these quantities. And we did this, we did a lot of experiments by changing the parameters values. And here are some examples of different driving velocity that we used, or different ratios between inertia of the plate and the spring, and values of the springs. These are some parts of the phase space, parameter space that we explored. And so let's start from what we found for the plate velocity distribution. Of course, the instantaneous velocity is a signal like this one, but if you make histograms for these quantities, you find some kind of irregularities, and has of course was also known from previous experiments, and so you may compute this distribution for different values of the parameters. Here is just an example for 3 different values of the driving velocities, and the same way you can compute the statistics of the slips by looking at the slip duration and the slip extension, angular extension, and you get some similar distributions, which are one-side distribution, but in this case you also find a peak, characteristic peak in size and time, which is not difficult to relate to the fact that you have a characteristic time in your system, which is the oscillation time of the spring inertia system. And so the position of the peak, you can change the spring and check that the peak moves accordingly. So, but what we wanted to do was to find a way of reproducing this data with some equation of some model. Usually models for stick slip motion, the more diffuse the investigated model in the past have been the Berich and Kropov models, which was introduced for explaining the intermittent dynamics observed in earthquakes and fault dynamics, or the Kontorova and Frankel model, which is employed for explaining friction between rough surfaces, between surfaces at a model level. And of course, both these models can produce a stick slip and different kind of stick slip from periodic to irregular, depending on the choice of the parameter of the model. But the problem with the chaotic motion in this model emerges essentially from the presence of many degrees of freedom which interacts in a nonlinear way. So you have chaos emerging from this model. At the same time, it's very difficult to relate the parameters of this model to the real situations because they are something intermediate between microscopic and macroscopic, and it's you don't know how to set the parameters of this model once you know the parameter of your experiment. So we decided to adopt a different approach. The different approach is different approach is okay. To try to, of course, to use the Newton equation of the system, in which you also include an unknown term, which is the reaction force of the granular system, and try to analyze this force to see which are the regularities of the features of these forces, of this force, which in principle can depend on any variable of the system, or also have memory terms or whatever. But actually things are not so complicated, luckily. So what can observe is that with a good approximation, F is of course a fluctuating quantity, but also has a little dependence on acceleration. So at the first starting point, one can choose to have a force which only depends on the position and on the velocity of the plate, and try to separate, to point out these dependencies. One has, of course, to make statistics. So if you look at the single slip event, you can see that the shear force as a function of the instantaneous velocity has a very irregular and complicated behavior, which seems difficult to describe. Of course, it is difficult to describe, but if you take many events and you make an average as a function of the shear force as a function of velocity, you get a regular behavior, which in some sense you can also expect it from a granular medium, which is a weakening of shear with the velocity, and then which is followed by a thickening when when you enter a fluidized regime. So you can assume this is a regular part of your shear force, which is not fluctuating and which is some regular viscous force, depending only on velocity. If you subtract this force from this force which is experimentally measured, you can find a signal of this kind, and this is of course the fluctuating part of the force, and so one can think of separating the force in a viscous part and in a fluctuating part. So you can also note this in this sense the motion of the disk is very similar to a Brownian motion of a particle, because in the Brownian motion you use a Langevin equation for description of the system, in which you have the viscous part, which is of course simpler than this one because just the Stokes term, and then there is a random noise which dominates the fluctuation, which rules the fluctuation. So for describing the viscous force, you can, of course, we don't have any ab initio indication. So you can use any expression which reproduce in a satisfactory way the observed data. And we adopted this expression, and of course you have to fit the parameters from the experiment. And okay, that was a plot in a linear scale. In a log-log scale you get this kind of curve, and you have linear decreases and then linear increases, increase of the friction. Then when, of course, you enter a square a regime which is square with the shear rate at higher driving velocity. Now, concerning, let's come to the fluctuating part of the force. Well, in a Brownian, the usual Brownian motion, the fluctuating force is just white noise. But in the case of a granular, we saw that this doesn't work very well, and the reason can be understood by thinking that reaction of the medium takes place via the formation of force chains, of course, as we know. And you can imagine that during the motion of the plate, the chains do not change completely from one instant to another, but just they change in a correlated way, because it will be just some chains will change, or just some part of the chains. So you can imagine that you can assume at the simplest level that the force in a given position is equal to the force at the previous position plus a small change, which is the random part, which is the noise. So in this case, you see that it is the force which is performing a random walk, which is the sum of independent contributions. And if you assume this behavior, you can write this kind of equation in which the derivative of the force is white noise. But of course, this would lead to a divergent force with the process, which cannot occur. And the way for avoiding this problem is just to bound the force with the potential to stay finite. And the simplest potential you can use is the square. Well, so you can add a linear bounding term to the force in order that the force performs a Brownian motion, but at the same time it is confined to stay to finite values. And in this way you introduce a correlation length, of course, in the force and in the process, and the correlation length can be estimated from the experiment. If you take the power spectrum of the force of the random part of the force after you subtract the viscous part, you get something like that, which is not, of course, is not a completely simple spectrum, but as a first approximation, you can neglect this peculiar behavior and just approximate the spectrum with the Lorentzian curve, which is the black line, which is, of course, is not a very good approximation, but in some sense reproduce at least qualitative features. And from this approximation, you can estimate the parameter A, which is the inverse correlation length of the force, and so that you can write the equation for the fluctuating part of the force, and try to simulate this process, which is you get just go back a moment. So finally you have this kind of equation, which takes the the aspect of a Langevin equation in which you have a deterministic part plus a force which has a viscous term, which is deterministic depending only on velocity, and a random fluctuating term which describes the randomness of the material. So what we got with this product by using the parameters of the experiment and those fitted from the experimental data for the spectrum and for the viscous force is that there is a good qualitative agreement with the experimental results for distribution of, I mean, not only qualitative, rather quantitative agreement for distribution of the velocity of the plate, for instance, and also for the distribution of the slip size or the slip duration. Of course, there are also disagreements, but the model can be certainly improved. And what we think is interesting, here is the reproduction of for different values of the ratio inertia of the disk divided by the spring, so you get different characteristic time from the systems, and you can see that the model reproduces also these characteristic times. What we think is interesting for this approach, which is, as I was saying, opposite to the deterministic chaotic approach, this is a stochastic approach to the problem, is that there are several other processes in which you can observe similar features, essentially in solid-on-solid friction or friction between polyethylene filaments, or there are also the nice experiment on sandpaper by Bomberger and co-workers, and in all these features experiments you can observe similar features on this in the stick slip motion. So one can think that similar equation, maybe with different random noise, of course, depending on the situation, can describe the process as well. So what we are doing now is to try to improve the description of the process by using a more refined law for friction, which is Dietrich and Ruina laws. We have a memory term that takes into account the aging of the contacts in the stick phase, and these are some preliminary results. And the other thing we are doing is to make experiments with different number of layers of beads. So here there are some preliminary results for you can see, for instance, the duration statistics with 0 layers or something like an increasing number of layers, 1, 2, 3, 4, and we are trying to see how this change the correlation in the system and how this can be described by the stochastic equation. And also one effect of changing the number of layers is, for instance, the change of the mean torque of the system, and also of the order parameter is just like was defined also in the yesterday, I think, or the day before, is the fraction of time that the system spend in slip phase or in the stick phase. So you can investigate. We are investigating how it does change with the number of layers. And I go to the conclusions. The conclusions are that the dynamical instability of of irregular stick slip motion can be described by a stochastic equation in which the force performs a Brownian motion itself, and that similar phenomenologies are observed in different systems. Of course, I think that the important point is to derive this these stochastic forces from ab initio or effective description of the granular medium. I mean, in all the system, but mainly in the granular medium, I think we believe there is the possibility of deriving the form of the force starting from more microscopic starting point. And the other important point, of course, is to try to compare the fluctuations that can be observed that are produced from deterministic model, which are usually employed for describing the stick slip and also the tectonic dynamics, for instance. Compare those fluctuations which are in nature deterministic with the fluctuation that can be produced by stochastic terms. That's all. Thank you.
I didn't get if it's at constant pressure. It's free to move vertically or not?
Okay, sorry. It is free to move vertically, so the pressure is constant and can be changed.